Hello students, from past few classes we are studying the paper Real Analysis First, and in the last class we have discussed about the number system, in which we have studied natural numbers, whole numbers, integers, rational numbers, irrational numbers, real numbers, and finally the complex numbers. All this we have discussed in detail in the last class. Now in the today's class we are going to revise one of the most important concepts, and it is the sets. In today's class we are going to revise the definition of a set, various types of set, various operations on sets, and so on. You are familiar with sets right from the 7th standard, and you have studied sets in detail time to time. In 11th and 12th standard also, you have studied sets, relations and functions in detail. And also, in the BSc first year, I have revised all these things in detail. Now in this class, we are just going to revise all the things whatever we have studied in the last year. So let us begin with sets. Definition of a set is: definition. A well-defined collection. A well-defined collection of objects. A well-defined collection of objects is known as a set. So, a well-defined collection of objects, we will call it as a set. Here in this definition of a set, the word well-defined is very important. By the word well-defined, we mean that if we have given a collection and if we have given some objects, then we should be in a position to tell that whether objects are members of that collection or not. If such collection is there, then that collection will call as a well-defined, and only well-defined collections will call as a set. Most of the times, a set is such a collection of objects that the objects which forms a set have some common property in them. They have some common property, whatever that property may be. Okay, so most of the times objects which forms a set have some common property in them, and using that property we are able to say that whether the objects belongs to that set or not. Next, objects which forms a set are called as elements or members of the set. Objects which forms the set are called as the elements of that set or members of that set. Members of the set. Elements or members of the set. Next, sets are generally denoted by capital case letters. Capital case letters such as capital A, capital B, capital C, capital D, and so on. Whereas objects which forms the set means elements of the set. Elements means the members which forms the set. They are denoted by small case letters. Small case letters such as A, B, C, D, and so on. Next, if X is a member of the set, member of the set capital A, then we write this as X belongs to A, and we read this as X belongs to A. X belongs to set A, or X is in set A. So in this way, this belongs to means the membership symbol is defined. Okay, this belongs to is called as a membership symbol. Next, if X is not in A, if X is not a member of set A, then we write this as X does not belongs to A, and we read this as X does not belongs to set A or X is not in A. If X is not a member of set A, then we write X does not belongs to A, and we read this as X does not belong to set A, or the same thing can also be written in short as X is not in A. X is not in A. Next we will discuss about some typical sets. Some typical sets. These are the sets that we frequently use. The first one is the set of natural numbers. So we reserve the letter capital N to indicate the set of natural numbers. Set of natural numbers. Which are natural numbers that we have discussed in the last class in detail. Next one, the set of integers is denoted by capital R. Set of integers. Obviously positive, negative, including 0. Next one, set of positive integers we denote by I plus or by Z plus. So, set of positive integers. Set of positive integers. Next one, set of negative integers is denoted by I minus or Z minus. Set of negative integers. Next one, set of rational numbers we denote by the letter capital Q. So capital Q denotes the set of rational numbers. Rational numbers. Next one, set of real numbers we denote by the letter capital R. Set of real numbers. And set of complex numbers we denote by the letter capital C. Set of complex numbers. In last class we have studied the number system in detail, and at that time also we have discussed about all these sets. Okay. To denote a set, we commonly use two methods. The first method is method of listing, in which we write all the members of the set separated by commas, that is in the form of a list. For example, if we have the set A and which consists of the members X, Y, Z, then this is one of the example of method of listing. Next one, suppose we have a set and that set is capital B and it consists of members A, E, I, O, U. Next one, suppose we have the set C which consists of members C equal to 2, 3, 5, 7, 11, 13, 17, 19. So, like such we have considered three examples of method of listing. Next one, the second method of representation of a set is the set builder method, in which sets are written by mentioning the common property of their elements. For example, the set B, which we have discussed just now, can also be written as B is the set of all X such that X is a vowel. Next one, Set C can also be written as set C is the set of all x such that x is a prime number. X is a prime number less than 20. Okay. There are infinitely many prime numbers. Of those less than 20 prime numbers, if we consider, then it gives the elements of the set C. So like such, we have two types of representation of a set. Next, we will discuss about the null set. Null set, also called as the empty set or void set. Null set or empty set or void set. As the name indicates, if we have a set which do not have any member in it, so a set having no elements, is called as a null set or empty set or void set. And we reserve the Greek letter phi to denote the empty set. So empty set is denoted by the Greek letter phi. Okay, or it is also sometimes denoted by empty parenthesis. This one. Example of this empty set is, suppose phi is the set of all n such that n is a natural number. N is a natural number less than 0. As we know that there is no one natural number less than 0, therefore obviously this phi will be the empty set. Next one, again suppose we have the set phi which is such that it is the set of all x belongs to R, means all real numbers x, such that x square is equal to minus 4. As we know that there is no one real number whose square is minus 4. Therefore, obviously, this second set phi will also empty set. So, like such, we have the empty sets. And empty sets are also important in our study. Next one is the equality of sets. Equality of sets. Suppose we have two sets A and B. Then we say that the sets A and B are equal if they have exactly same elements. If two sets A and B have exactly same elements, then we say that the sets A and B are equal. And then we write this as A is equal to B. Okay, A is equal to B. For example, A is the set of all prime numbers less than 10. Then the set A will be 2, 3, 5, 7. So this will be the set A. And suppose B is the same set if it is written in the roster form. Means B is the set of all x such that x is prime. X is the prime number. Okay. And x is less than 10. Then from this it is clear that we have A is equal to B. Like such, the equality of sets is defined. Next one is the finite and infinite sets. Finite set. If a set has finite number of elements in it, then we call it as a finite set. So set having finite number of elements. Is known as the finite set. By the finite number of elements, we mean if we start number of elements in the set then the process of counting elements should end at some stage. Then such sets are called as the finite sets. Next one is the infinite set. Infinite set. A set which has infinitely many members. Infinitely many elements is known as the infinite set. Okay, so set having infinitely many members is known as the infinite set. For example, if we consider the set of all natural numbers, then if we start counting elements in this set, then the process of counting never ends. Then clearly this set has infinitely many elements in it, therefore it is infinite set. Here it is to be remembered that the empty set phi is a finite set. Finite set. Next one, if we have a set A which comprises of only one member, and suppose that member is 8, whatever the member may be, then such set is called as a singleton set. Singleton set. A set which has only one element in it is called as a singleton set, or also called as a one-point set. One-point set, as it has only one element, means only one point. Next one are some commonly used notations. These notations we use frequently. The first one is there exist. It is denoted by this notation, there exist. There exist. This notation we use to denote there exist. Next one, for all. It is denoted by this notation, for all. Next one, implies. To denote the implication, we use this notation. Next one, to denote the implied by, we use the notation which is this, implied by. Next one, we use the notation, this one notation, to denote if and only if. If and only if. And this is also for implies and implied by, means for the double implication. Next one, we use the notation, this one notation, to denote and. Next one, we use this notation V to denote or, and we use the notation tilde. This symbol is called as a tilde, T-I-L-D, tilde. This symbol is tilde, and this notation is used to denote not. Not means negation. So like such, these notations we use most of the times. Now next one, we will discuss about subsets. Suppose if we have two sets A and B, such that if each element of set A, if each element of set A is also in set B. If each element of set A is also in set B, then we say that A is a subset of B. A is a subset of B, and we write this as, means in symbols we write this as A is a subset of B. Okay, so like such the subset is defined. Next one, if A is a subset of B, then we also call it as A is contained in B. A is contained in set B. Next one, If A is a subset of B, then sometimes we also say that B is a superset of A. B is a superset of A. Or in this case, we also say that B contains A. B contains A. So, contained in and contains. Don't confuse between these two words, contained in and contains. So, if A is contained in B, then it means that A is a subset of B. And B contains A means B is a superset of A, means A is a subset of B. Okay, so this one. Next one, if A is a subset of B, then there are two possibilities. The first possibility is that A may be equal to B, and the second possibility is that A is not equal to B. Okay, so we'll consider the next one as the proper subset. Proper subset. If A is a subset of B and A is not equal to B, which means that every element of A is in B and B has at least one element which is not in A, then in this case we say that A is a proper subset. A is a proper subset of set B, and we write this as A is properly contained in B. Okay, in this case we also say that A is properly contained in B. A is properly contained in B, or B properly contains A. Both means the same. Okay, next one. Now it is clear that if A is a subset of B and B is a subset of A, then this implies and is implied by. This implies and is implied by A equal to B. Means this is possible only when A and B are one and the same sets. Okay. If we have two sets A and B such that each one of them is a subset of the other, then the sets are equal. This is important as many times to prove that two sets are equal, we have to show that each one of them is a subset of the other. Next one is the comparable sets. Comparable sets. Suppose if we have two sets A and B such that either A is a subset of B or B is a subset of A, then we say that sets A and B are comparable. If A is a subset of B or B is a subset of A, then we say that sets A and B are comparable. And from this definition, it is clear that two sets A and B are not said to be comparable, means they are non-comparable if A is not a subset of B as well as B is not a subset of A. Next one we will discuss operations on sets. Operations on sets, in which we are going to study union, intersection, complement and difference of sets. So to begin with is the union of a set. Union of sets. Let A and B be two sets. Then a set which consists of all elements of set A and set B is called as the union of sets A and B, union of sets A and B, and it is denoted by A union B. So in symbols, the same thing we can write down as A union B is the set of all elements X such that X belongs to A, or X is in B, or X is in both A and B. X is in both A and B. So if X belongs to only A, then it is a member of A union B. If X is a member of only B, then also it is a member of A union B. And if X is in both A and B, then also X is a member of A union B. So like such, the union of two sets is defined. From the definition, it is clear that we have A union empty set is equal to A. If A is any set, then union of A with the empty set phi is always A. Next one, we have union of any set with itself is equal to the set itself. Next, if we have A as a subset of B, if A is a subset of B, then union of A and B gives us the set B. Next one, we have A union B, same as B union A. Like such, we have the properties of union of sets. Next one is the intersection of sets. Intersection of sets. Intersection of sets. Let A and B be two sets. Then the set consisting of only those elements which are in both A and B, which are in both sets A and B, that is, only common elements. Then that set is called as a intersection B. That set is called as intersection of A and B. And it is denoted by the symbol A intersection B. So like such, we have the intersection of two sets. So the same A intersection B can also be written in symbols as A intersection B. It consists of all the elements X such that X belongs to A and X belongs to B. Here we are using the word AND. So AND means both the conditions should be satisfied. So if X is in both the sets A and B, then only it will be the member of the intersection A intersection B. From the definition of intersection of sets, it is clear that we have A intersection phi is equal to phi. Means if A is any set, then intersection of empty set with set A is always the empty set. Next one, we have intersection of any set with itself as the set itself. Means A intersection A is equal to A. Next one, we have A intersection B is equal to B intersection A. A intersection B is equal to B intersection A. Next one, if A is a subset of B, if A is a subset of B, then A intersection B is same as the set A. Also from above definitions, it is clear that A is always a subset of A union B. A is always a subset of A union B, as well as B is also always a subset of A union B. But if we consider the intersection, then A intersection B is always a subset of set A, as well as A intersection B is always a subset of set B. Next one, we'll discuss the disjoint sets. Disjoint sets. Suppose if we have two sets A and B, such that they do not have any element in common. Okay? If two sets A and B do not have any element in common, which means that A intersection B is equal to the empty set phi, then we say that the sets A and B are disjoint. Now, if the sets A and B are such that, their intersection is non-empty, means A intersection B is not equal to phi, their intersection is non-empty. Okay, then we say that A and B are non-disjoint. They are non-disjoint. Or we also say that A and B are overlapping. They are overlapping sets, means they are non-disjoint sets, means they have at least one point in common. They have at least one point in common. Next one, universal set. Universal set. While studying sets, it is usually assumed that all the sets are subset of a very large set. Then that large set is called as a universal set, and it is generally denoted by the letter capital U or capital X. Universal set is generally denoted by capital U or capital X. And in the real analysis, we consider the universal set as the set capital R. If A and B are any sets, and if we are studying the operations on sets A and B, then it is assumed that A as well as B both are subsets of the universal set. Next one is the difference set. Difference set. Let A and B be two sets. Then the set consisting of those elements of set B which are not in set A, is called as the difference set. Difference set of A and B, and it is denoted by the notation B minus A. So in this way, difference set is defined. Next, if the set A is a subset of the set B, means that is, if A is a subset of B, then the difference set B minus A is also called as the complement of A in B, or the complement of A with respect to B. Complement of A with respect to B. Next one, complement of a set. If A is a subset of the universal set, if A is a subset of the universal set U, then the difference set U minus A is called as, then the difference set U minus A is called as the complement of A, or the complement of A with respect to universal set U. We simply call this as the complement of A. Okay, complement of A. So the difference set U minus A is called as the complement of A, and it is denoted by A complement. Most of the time we denote it by the A complement. Sometimes to denote the complement of A, we also use the notations as A bar or A dash. But here in this paper, we are going to use the notation A complement to denote the complement of set A. From the definition of complement of set, we have some properties of complement, and the properties are: we have A complement is equal to U minus A. Next, we have A union A complement. A union A complement is equal to the universal set U. This is the universal set U. Next, we have intersection of A and A complement as the empty set. A intersection A complement is the empty set phi, as there is no one element which is common in set A and it's a complement. So today we have discussed about sets in detail. We'll stop here, and in the next class we'll discuss about Cartesian product of sets and relations and functions. Till then, we'll stop here. Thank you.